Okay, the topic of today's lecture is change of coordinates. This lecture was actually originally lost, so I will re-record it now after our quarter is over. And actually there's no one in my audience, it's just me talking to the camera, so I think it'll go a little bit faster. Change of coordinates. So in the previous lecture, you saw that objects that are calculated similarly in different coordinate systems actually end up being different objects. For example, the covariant basis. The covariant basis in Cartesian coordinates is two vectors I and j, unit vectors at the 90-degree angle to each other. In polar coordinates, it's a totally different set of vectors. It's still orthogonal, but the vector that corresponds to the coordinate r is the unit vector that points in the radial direction. And the basis vector that corresponds to the coordinate theta is orthogonal to the first one, but its length is not unit, its length is r, and it points in the tangential direction to the circle. So, same algorithm, but in different coordinates that leads to different objects. Our ultimate goal is, of course, to come up with a way and a set of objects that are invariant, where identical algorithms in different coordinate systems actually lead to the same object. Those objects would be called invariant, and it is those objects that are meaningful geometrically and physically. Maybe one of the most important objects of that kind is the gradient. We still don't have a proper definition of the gradient. The definitions that we've come up with so far depend on the coordinate system. And if an object depends on the coordinate system, then it's not really reflective of the physical reality or the geometric reality. It has as much to do with the coordinate system as it does with the reality that it's trying to describe. So our ultimate goal is invariance. How are we going to achieve invariance? We will first study how these types of objects called variants, which are obtained by a similar rule in various coordinate systems, how they depend on the coordinate system. In other words, we'll study how it changes with a change in coordinate systems. So in this lecture, we'll just concentrate on coordinate changes of coordinates, and just discuss them. And then in later lectures, especially once we're armed with the tensor notation, we'll actually discuss how objects change from one coordinate system to another. And we'll discover that some objects change from one coordinate system to another in a very, very special way. And those objects will be called tensors. But for now, let's concentrate on changes of coordinates. So here we'll just consider an example. We'll talk about Cartesian coordinates and polar coordinates and a relationship between them. And we'll discover one very important characteristic of the relationship between them. So, Cartesian coordinates. We'll denote Cartesian coordinates by x and y. And we have drawn the coordinate lines that correspond to Cartesian coordinates before. And we'll also look at polar coordinates, r and theta. And we've described what r and theta are in a previous lecture as well. Now, these of course are connected because they're imposed on the same Euclidean space. There's a connection between x and y and r and theta. And you're very familiar with that connection. Let's first talk about x as a function of r and theta. That relationship is usually written this way. X equals r cosine theta. And then looking just a step ahead, we have to be very careful with interpreting this type of expression, because we're going to take derivatives of this expression. So what x is here is actually what the letter x represents is a function of r and theta. And as a function of r and theta, it can be differentiated with respect to r and with respect to theta. So in order to highlight that fact, we will actually write this relationship the following way. We will write x as a function of r and theta. So you see that x in this identity represents a function. Y as a function of r and theta is r sine theta. There's, of course, an inverse relationship as well. R and theta can be expressed as functions of x and y. And these are very familiar expressions. R as a function of x and y is square root of x squared plus y squared. All right, these two functions won't be as nice as these two. Square roots are not particularly nice. And then theta as a function of x and y, it's usually written as arctangent of y over x. That's because dividing y by x gives us tangent theta. So theta is arctangent of y over x. But arctangent is a funny function. For example, if both x and y, if the point is in the third quadrant at, let's say, 5 pi over 4, then y over x will be 1, and if you evaluate arctangent of 1, any calculator will probably say pi over 4. So keep in mind that when people write arctangent of y over x, what they really mean is this function that should really be written this way. Arctan of x comma y, which is cognizant of the fact that sometimes it's a different angle. And this function is every bit as good as this function in terms of taking derivatives and so forth. But we'll stick with this function and realize that that's what it means, that sometimes the angle calculation is a little bit more nuanced. Okay, so what do these relationships, what are some of the interesting properties of these relationships? Well, we'll concentrate on just one, and it's the fact that these relationships are the inverses of each other. Let's write down what it means. It means that, for instance, if we took these expressions for x and y in terms of r and theta and plug them into this expression, what we'll recover will be r. And if we substitute it into this expression, more accurately into this one, y over x is tangent theta, arctan of tangent theta is theta. It would be even more clear with this function. We recover theta. That's what it means to say that these sets of functions are the inverses of each other. And here, of course, it's r squared cosine squared theta plus r squared sine squared theta. R squared comes out as r. Under the radical, we have cosine squared theta plus sine squared theta, which is 1. So r. So these relationships can be written in the following way. R as a function of x and y. But let's plug into the function of x and y the expression for how x and y depend on r and theta. So if we plug in x as a function of r and theta, and y as a function of r and theta, as we just saw, we would recover r. And that's a very tricky identity. Well, I take it back. It's not tricky at all. But the notation makes it subject to misinterpretation. So when you look at an identity like this, and it might even be better to write a triple equal sign. When you look at an identity like this, you have to be very clear to yourself which letters represent independent variables and which letters represent functions. And sometimes the same letter represents two different things in the same identity. And it's up to you to keep it straight. For example, r on the right-hand side here is the independent variable. It's the same independent variable as in these two functions, because it is these two functions that are plugged in here. So r right here is the independent variable, and r is the independent variable. However, x and y are not independent variables here. X and y denote these functions. And this r is not the same as this r. This r is a function of x and y that is square root of x squared plus y squared. So these two r's are different. This r is a function, it's this one. And this r is the independent variables from these two functions. So we could have made it less ambiguous if we introduced more letters, but experience shows that introducing more letters actually leads to a little bit more confusion. So it's better to use fewer letters, but interpret the context correctly. Let the context dictate the meaning of each variable. So independent variable, independent variable, independent variable, independent variable, and the result is r. So this is an identity in r and theta. This is true for all r and theta, as we saw by just plugging it in. So these expressions can be, for instance, differentiated with respect to r, this identity, as we'll do shortly. Okay, let's write down the same thing for theta. So if we take this function and plug into this function, form a composite function of how x and y depends on r and theta, we'll recover theta. So theta as a function of x, where dependency of x and r and theta is plugged in, and y identically equals theta. So this is the algebraic expression of the statement that these two sets of functions are inverses of each other. We could have gone the other way as well. We could have plugged in these functions into these functions. And here's what we would have. X as a function of r and theta, but plug in how r depends on x and y, and how theta depends on x and y, and you will recover, well, I think you can guess by now, but let's just see what would happen. Plug in, well, it wouldn't be so easy to see. Plug in x squared plus y squared for r, and plug in arctan of y over x for theta. You would have to find the cosine of the angle whose tangent equals y over x. And of course, the cosine of that angle is x divided by square root of x squared plus y squared, which would cancel this square root of x squared plus y squared. And the result will be x, just like we could have guessed. Not as easy to see, but pretty much the same thing. And of course here, we would get y. So that's an alternative statement. It's just an alternative way of writing down the fact that those two sets of functions are the inverses of each other. So that's how changes of coordinates are usually specified. You can go from one coordinate system to the other or backwards. So we of course could have obtained these functions from these functions by solving for x and y. If we take this as a set of equations where r and theta are given and x and y are unknown, and we were to solve for x and y, of course we would obtain these equations. So that's how changes of variables are specified, either by this set of equations or by the inverse set of equations. And here we just wrote down the mathematical expression for the fact that these sets of functions are the inverses of one another. I'll now erase the board and we'll talk about the Jacobian of a coordinate transformation, which will be a set of partial derivatives of these functions. Okay, let's talk about Jacobians of coordinate transformations. A Jacobian is essentially a matrix of partial derivatives. So for instance, let's talk about, once again, polar and Cartesian coordinates, and talk about the transformation of Cartesian coordinates to polar coordinates. So for example, x as a function of r and theta is r cosine theta. Y as a function of r and theta is r sine theta. And of course, the terminology is debatable, whether this is a transformation from polar to Cartesian or from Cartesian to polar. I think perhaps this would be best to call from polar to Cartesian, because given polar coordinates, it will give us the value of the corresponding Cartesian coordinates. And let's consider the matrix of partial derivatives of these two functions with respect to the two sets of, with respect to the two independent variables. So there will be a total of 4 entries in the Jacobian matrix. dx dr, dx d theta, dy dr, dy d theta. And of course these numbers are naturally organized in a 2x2 table. That's because we have 2 dimensions. In 3 dimensions, it would be a 3x3 table and so forth. Let's make it a little bit larger. So that everything fits. All right, several things to pay attention to. Number 1. All right, so let's put what these entries are. So it will be dx dr, which is cosine theta. So the first thing to realize is that the functions, the expressions that will go into this matrix will naturally appear in terms of r and theta. And when we deal with the opposite transformation, the matrix will consist of a bunch of x's and y's. So that's just something to keep in mind. And dr d theta is minus r sine theta. So if dx dr and dx d theta go in row 1, dy dr, dy d theta will go into row 2. dy dr is sine theta. Maybe this matrix didn't need to be so large. And dy d theta is r cosine theta. This matrix is usually denoted by writing x and y parentheses on top, divided by r and theta on the bottom. But we'll come up with better notation when we discuss the tensor notation. So let's not have any notation for this matrix. But here's the Jacobian for the polar to Cartesian coordinate transformation. Now let's also talk about the Jacobian for the inverse transformation from Cartesian to polar. So r of x and y equals square root of x squared plus y squared. You might be wondering what's the point of Jacobians? So I won't answer that question now, except that the Jacobian will feature very prominently in our discussion on how objects change from one coordinate system to another. And there will be another, perhaps an even more important object, which corresponds to second-order derivatives. Of course, there are 8 second-order derivatives. Each of the variables, each of the functions, with respect to each pair of the independent variables. So it will be 4 plus 4, 8. So that's where these objects will become important. In this lecture, we're not going to use them. We're just going to write them down and notice one very special property. So back to this. Theta of x and y, I'll still write it as arctan of y and theta. If you're worried about, y over x. If you're worried about certain quadrants, then let's just limit this discussion to the top right quadrant. But this actually remains valid in all quadrants, if only you replace this arctan with a more intelligent arctan that takes 2 inputs. Okay? All right, let's consider the Jacobian here. Okay, dr dx, a pretty good exercise in partial differentiation, but it ends up being x over square root of x squared plus y squared. Similarly, dr dy is y over the square root of x squared plus y squared. Arctan of y over x So I don't remember what it is, so we're going to have to derive it. The key thing to remember is that the derivative of arctan as a standalone function is 1 divided by 1 plus its argument squared. So I'll try to do it in my head. So the derivative of this with respect to x, alright, so much for doing it in my head. 1 plus y over x squared times the derivative of y over x. And of course the derivative of y over x is minus y over x squared. X squared will cancel, so the result is negative y over square root, excuse me, no square root, over x squared plus y squared. Over, I'll write it in a moment. This, by similar calculation, will be x divided by x squared plus y squared. And now this spot is dry, so I can write this in x squared plus y squared. So that's the Jacobian of the reverse transformation. And now I just want to notice one very important relationship between these two Jacobians. What turns out is that these two Jacobians are inverses of each other in the matrix sense. This matrix is the inverse of this matrix. Of course, they need to be compared at the same physical point, where x and y corresponds to the same point as r and theta. So let's test that, make sure that it's true, and then try to figure out what's the fundamental reason behind this. Okay, so let's see. So in order to do this, we're now observing something that I mentioned just a moment ago, that this is a function of r and theta, and this matrix is a function of x and y. That makes them hard to compare. So we'll have to convert them to the same coordinate system. So I'll make one choice, and then for exercise maybe you want to do the opposite choice and do it that way. I'll convert both to polar coordinates. So this matrix can be rewritten unchanged. This is our trying to multiply them together. Well, not trying, I'm sure we'll succeed. This will be the result. This matrix can be rewritten unchanged. Cosine theta. You needed better planning. So I will write slightly smaller. Again, I'll let the spot get dry. So here we have y, well, I'm just rewriting this right now. Okay, so sine theta, r cosine theta, and negative r sine theta. So that's the first matrix we're written unchanged. Now let's convert this to polar coordinates. Here we have x is r cosine theta divided by r. So that's just cosine theta, and this is sine theta. Cosine theta, sine theta. Let's see what happens here. On the bottom we have r squared. On top we have minus r sine theta. So it'll be minus sine theta divided by r. Minus sine theta divided by r, and the other one is cosine theta divided by r. Okay, now let's multiply these two matrices together. Let's see what this entry is. It'll be cosine squared theta, and then the two r's cancel, minus sines give you a plus. Cosine squared theta plus sine squared theta, 1. Let's move on to this entry. Let's see. Cosine theta times sine theta. Once again, r's cancel, so we have cosine theta sine theta minus cosine theta sine theta. So 0. Let's move on to this entry. Cosine theta sine theta minus cosine theta sine theta. 0. And the last entry is sine theta times sine theta, sine squared theta, plus cosine squared theta. A very satisfying result. The result is the identity. So indeed, the two Jacobians corresponding to the same point for the inverse coordinate transformations are matrix inverses of each other. And the obvious question is why? Why is this so? So I'm about to erase the board and show why this is so. Of course, it is somehow a consequence of these two sets of functions being inverses of each other. And as just about everything that's great in life, this result will be obtained by differentiation of an identity. So let me erase the board and see how that goes. All right, let's see how it's done. This discussion will actually be quite general and will apply to an arbitrary transformation in 2 dimensions. I will continue to say r and theta, x and y, but you can think of them as not necessarily polar coordinates and Cartesian coordinates, but there's one coordinate system and an alternative coordinate system. And we'll never make references to radii or cosines or any of the Cartesian coordinates. But we'll still say r, theta, x, and y just to have concrete letters. So let's actually start on the right-hand side and rewrite our matrices that we had on the board before in general terms. And by that I mean, forget the fact that r, theta, and x and y are polar and Cartesian coordinates. But now let's just think of them as two general coordinate systems. So the first matrix was dx dr, and we'll actually write it in abbreviated form. So we'll just write x sub r indicating dx dr. So it's dx dr, dx d theta, dy dr, dy d theta. And this matrix was the inverse, quote-unquote, relationships. So dr dx, dr dy, d theta dx, d theta dy. And again, reminder, don't think of these as polar and Cartesian coordinates. Think of these as two general coordinate systems. Now, even for the two general coordinate systems, we can write down the mathematical expression for the fact that the two coordinate changes are the inverses of each other. So let's write this. Let's say that x as a function of r and theta, where into this relationship we plug in how r depends on x and y, and how theta depends on x and y, and the result is x. And my square x's and curvy x's are the same letter. If I write things slowly, I go for this x. If it's a little bit faster, I write this x. And the second relationship is the same thing for y, as a function of r, of x and y, and a function of theta, of x and y, is y. And let's remind ourselves that these are actually identities in x and y. So we'll write the triple equal sign. And another reminder that in the let's say in the first relationship, the letter x plays two different roles. This x represents a function of r and theta. That function may be r cosine theta if these are Cartesian and polar coordinates. This x, and the x on the right-hand side are the independent variables. Same thing here. Y has two different meanings. This y is a function of r and theta, maybe r sine theta. This y is the independent variable, as well as x. And here y is also the independent variable. While r and theta are not the independent variables, they represent functions that are used to represent coordinate changes. So it might be square root of x squared plus y squared, and arctan of y over x, or a more general coordinate change. So how would this identity be obtained? Well, of course it comes from these statements, because these are the statements that relate these functions to these functions. So to somehow somehow it must be a consequence of this. And as so often in this course and in life, it can be obtained by partial differentiation. And there are 4 partial derivatives that we can take here. So the first identity is an identity in 2 variables, x and y. So it can be differentiated with respect to x, and it can be differentiated with respect to y. And the second identity can be differentiated with respect to x, and can be differentiated with respect to y. So let's find these 4 derivatives. And of course we have composite functions all over the place. X is a function of r and theta, but we'll plug in how r and theta depends on x and y. So this is a composite function in x and y. So when there are composite functions, there are chain rules. There is the chain rule. So the chain rule will be used over and over again in this derivation. So let's get to it. So let's first differentiate this identity with respect to x and see what we get. So here's how it's going to go. By the chain rule, well, forget about the chain rule. Let's look at the right-hand side first. So x is the independent variable. So differentiating this identity with respect to x leaves 1 on the right-hand side. It's a good start. Let's see what we get on the left-hand side. So this is where the chain rule comes into play. The left-hand side, the derivative with respect to x, will read dx dr, dr dx, plus dx d theta dx, and that'll equal 1. So let's write down what we just said. Dx dr, dr dx, plus dx d theta dx equals 1. Okay, so once again, time to be very careful. I did not mean for these 2 x's to be different. Okay, this x represents the function of r and theta. This x is the independent variable. So you have to be constantly aware. I usually continuously explain to myself, what does the variable that I'm looking at represent? If you don't do that, if you just approach it as a formal exercise, then you will find nothing but pitfalls. Because if you wrote this in different notation, if you wrote this as dr dx, dx dr, you might be tempted to cancel dx, cancel dr, and you'd think that's 1. Dr dx, dx dr almost looks like 1. But of course it's not. That would be completely nonsensical. That would be an example of calculus notation leading you astray. Never happens in tensor calculus, but right now we're just doing conventional calculus with conventional notation, so time to be careful. Okay, dx dr, dr dx, plus dx d theta dx equals 1. That's chain rule. But now let's come over here and see what this entry is. It is dx dr, dr dx, plus dx d theta dx. So we just proved that it's 1. So before we saw that it was 1 in our particular example of Cartesian to polar. But now we see that, but we didn't know why. Now we see why. It comes from differentiating the first identity with respect to x. And it's just wonderful that this identity of first-order derivatives can be encoded perfectly in the language of matrices. Let's now differentiate this first identity with respect to theta. And on the right-hand side, of course, we'll get 0, because this only depends on x and not on y. And on the left-hand side, we'll have, we're now differentiating this identity with respect to theta. I think I said, there you go. We're now going to differentiate this identity with respect to y. I believe I said theta. This was differentiating it with respect to x. We're now going to differentiate it with respect to y. So we will have dx dr, dr dy, dx dr, dr dy, plus dx d theta dy, plus dx d theta dy, and the result is 0. Great. Now let's see where this finds itself. So it's dx dr dy plus dx d theta dy. So it's this entry. So we've now shown quite generally that this entry is 0. Let's just knock out the other two. The other two, the second line, comes from differentiating this identity. So let's differentiate this identity first with respect to x, giving us 0 on the right-hand side, and then with respect to y, which will give us 1 on the right-hand side. So first with respect to x, dy dr dx, that's chain rule, dy dr dx plus dy d theta dx. Let me spread it out so it matches. Plus dy dr plus dy d theta dy equals 0. dy dr. All right, let's do it again. Differentiating this identity with respect to x, 0 on the right-hand side, I'm about to fix this. dy dr dx plus dy d theta dx equals 0. Great. Let's find it here. dy dr dx plus dy d theta dx equals 0. So now you're beginning to have the sense that this is not about Cartesian, polar, or 2 dimensions. This is quite general. But the chain rule pretty much tells us that the two Jacobians are related by the inverse relationship. So the last one is dy dr dy plus dy d theta dy equals 1. And of course that belongs here. Let's just make sure of this. dy dr dy plus dy d theta dy equals 1. So what first seemed like a wonderful coincidence, we now see as a very regular fact to be expected because we demonstrated where it comes from. And you can intuitively tell, of course, that this is not limited to 2 dimensions. This would be true in 3 dimensions, and nothing in this derivation relied on polar and Cartesian coordinates. So this would be true for any 2 general coordinate systems and expressions relating one to the other. And I think it's pretty clear. However, we will use this very calculation and our attempt to generalize it to arbitrary dimensions, even though you can pretty much see that this will hold up in higher dimensions as well. However, in the next lecture, we will use this as an excuse to introduce the tensor notation, which is wonderful in many ways, but one of the ways in which it's wonderful is that it makes this calculation, it can capture this entire calculation for arbitrary coordinates, in arbitrary dimension, a one-line exercise. And of course, compactness is not the only benefit of the tensor notation, but it's one of the benefits. So we will see that front and center in the next lecture. Let's see. I think that's it. I think now the lost lecture has been recovered, and now the playlist on YouTube will flow much more logically. Thank you.